Okay. Good evening, everyone. Uh, Once again, my name is Saida Sheikh, and I'm one of the TAs for soil mechanics course for NPTEL, and this is our interactive session number 7. And today we will be covering topics on shear strength of soil. Some of it we did last time, but that was very basic. We studied about the Mohr circle. Today we will do some questions on direct shear test, triaxial test, um, maybe an confined compression test. And this is what has been covered in week 7, and we will be doing some questions on this. So let's move on to the first question. Just a moment. Okay. So okay. So the first question is for direct shear test. As you know, if we recapitulate a little, there are two kinds of tests for shear strength that we conduct. There is a direct shear test, usually done for coarse grained soils, and this is quite straightforward. It is very rapid. It's a rapid test, but it's not as comprehensive and detailed as the triaxial test. Uh, and this usually, as I mentioned, we do for getting some updates. That's why my laptop is a little slow. Just bear with me for 2 minutes. I will reschedule these updates. Okay. So in the direct shear test, we have this apparatus in which we have a cuboid with an upper box and a lower box, and we fill this entirely with the sample, and we place a normal load over this, and with the help of a mechanism we start, this is stationary, and we start pushing this, and on this plane, on this predetermined plane, failure plane, we can calculate the C and the phi. Usually, since it is performed for coarse grained soils, usually it is done for soils with C equal to 0. So we are more comfortable in calculating phi of coarse grained soils in this apparatus. So we have been given some data. The direct shear tests were performed on dry sandy soil. The size of the specimen was 2 inch into 2 inch into 0.75 inch, which means it is 2 inch in this direction, 2 inch in this direction, and the height is 0.75 inch. So the area of the failure surface will be initially 2 into 2, which is 4 inch. Okay, so we have been given the normal force, we have been given shear force at failure, and what we need to do is find the shear stress parameters. Write it here. Are given below. Find the shear stress parameters. So for that, let's go to our Excel sheet. Okay, let's create an Excel sheet for calculations. Let's call this interactive session 7. Okay, so we have been given, let me take this data, all of it. Okay, the area of the failure plane is, we know the area is 2 into 2, that is 4-inch square. Let's convert to, wait a moment, let's convert this to feet square. This is in, sorry, this is in pounds again. So the normal force will be, let's call this, the side is 2-inch, which is equivalent to 1 into 1 by 12 feet. So the area will be this multiplied by this, which is equivalent to this multiplied by this in feet square. Okay, so the normal stress will be force by area, which is force over area. Let's fix this. Actually this should be area. Okay, let's fix this. This will be 720, and let's write the units here, which will be pound per feet square. So what we are doing right now is we are calculating the normal stress, which will be, stress is force over area, and we will calculate the shear stress. Let me remind you why we are doing that. We are doing this because this is this over, sorry, area. This will be 432. These are the values of shear stress and normal stress. Why we are doing this is because when we want to calculate in direct shear test, we calculate the shear force. Okay, we calculate the shear stress, the shear normal stress, and then we plot a graph between normal stress and shear stress. Then we plot the points for at a given normal stress. What is the shear stress at failure? At a given normal stress, what is the shear stress at failure? And we get an envelope kind of thing, isn't it? Isn't that what we get? The x-intercept, I don't know why it's coming out to be so ugly. Let me try again. So I take this, okay, and I calculate I at a particular normal stress and shear stress, at a particular normal stress and shear stress. I have these 2 points. I connect these. I pass them through the y-axis. This part here gives me the cohesion, and this angle here gives me the friction. So that is what we did. We knew the normal force. Based on this, we calculated the normal stress, and we knew the shear force. Based on this, we calculated the shear stress, and now we are going to plot. Okay, so let's plot. On the x-axis, we will have normal stress. On the x-axis, we will have normal stress. On the y-axis, we will have shear stress. Okay, let's call this direct shear test curve. Okay, okay, and let's now draw a trend line. Not the legend, the trend line. We will display the equation. Into linear trend line. Let's display the equation here. Okay, it's almost going through the zero intercept. Let's call it through a zero intercept. So we will have y equals 0.602x. So we have y equals 0.602x. Now y here is tau equals 0.602 sigma dash. We know the equation. You know the equation tau is equivalent to C plus sigma dash tan phi dash. Now C equals 0 here, then tau equals tau by sigma dash equals tan phi. Okay. Um, Tau over sigma dash. So here tau over sigma dash, that means tan phi equals 0.602. And let's calculate tan inverse. Okay. Tan inverse 0.602 comes out to be approximately 31 degrees. So our phi dash is equal to 31 degrees. Okay. So here we can actually write this is equivalent to A tan of 0.6016, but we need this in degrees. So we will do degrees anti-tan of this comes out to be 31 degrees. This is 5. Okay. This was the question number 1. So let's move on to question number 2. Let me highlight it here. This is the answer. Okay. So the next question. Following are the results of 4 drained direct shear tests of an overconsolidated clay. See, these are drained tests of OC clay. The diameter of the specimen means that this is cylindrical. I don't know why they have written direct shear test, but this seems like a triaxial test. The diameter of the specimen is 50 mm. Height of specimen is 25 mm. Okay, will be something like more like this. This will be way shorter than your normal triaxial. This 25 mm. Determine the relationship for peak shear strength and residual shear strength. We have been given shear uh, force at failure and shear force at residual shear force. As you know, when we draw, when we calculate or when we load a soil, the shear force will first increase, then it will decrease, and then it will reach a steady value. Even the this is our residual shear force strength, shear stress. This is our shear stress at failure. This will be our sigma. Okay, so now let's go back to our Excel sheet. This is question number 2. We have been given normal force, shear force, and residual shear force. Okay, and diameter has been given 50 mm, height has been given 25 mm. So the area of failure plane will be, since this is still a direct shear test, we will have some kind of mechanism that will create this kind of shearing in the specimen such that this comes out to be the failure plane. This will just be like the top surface of the specimen, and the area, this will be the area at of failure plane, which is simply pi into r is 25, 25 pi into diameter over 4 pi r square, isn't it? But let's do one thing. Let's write, oh, let's try 22 by 7. Okay, sorry. Let's write these in meters. This will be in meter square. And this will be 0.05. This will be 0.025. And this will be our area in meter square. Then our normal force, as in sigma in kilonewton per meter square, will be force divided by 1000 for kilonewton and area. Okay, this will be our normal force. Oh, okay. Actually, I should have chosen this. Okay, And let's calculate for shear force and residual force. This will be C2 over 1000 divided by area 2. Okay, this is fine. Let's write this in the bottom. Sigma n, this will be tau f. This will be tau r, and everything is in kilonewton per meter square. Now we have our values of sigma, tau r, and tau f. Now let's plot them. Let's call this shear at failure plane. X-axis will be sigma, y-axis will be at failure. Okay, now we will add, this will be a residual shear. Okay, x-axis will be again sigma, and our y-axis will be tau. Okay, uh, okay, let's draw trend lines. Actually, let's convert these into only scatters. Okay, so we can add trend lines. Yes, let's add a trend line here also. Okay, and that's better. So this will be, let's add a legend. That's better. And now we will mm, 5 periods, 50 periods. Oh, 100 periods. Okay, that is better. And let's forecast this backwards again. This is at 76, so 75 periods, and this is at, which is also at 75. Let's forecast this back at 75 periods. Okay, so this will be our shear strength at failure. It will have an intercept as well as um, a slope, and this is our residual shear. And now let us see the equations for these. Display equation on chart as well as for this display equation on chart. Okay, uh, let us set an intercept of 0 for this one. Okay, so for residual shear, for shear at failure, we have a C value of 38.2, and we have a tan phi value of, or we can say a phi value of, this will be degrees, a tan of 0.5217. This will be 27.5 degrees. And residual shear, we will have C0, and this will be, let's copy this, 0.2672. This will be 15 degrees. Okay, let's transfer this to our slides now. So our tau f came out to be 38.2 plus sigma dash tan of 27.6 degrees, or CF is 38.2 and phi f is 27.6, while our residual shear stress came out to be sigma dash tan of 15 degrees, 115 degrees, or our residual angle of friction will be 15 degrees. So these are the peak shear strength and residual strength relationships for peak shear strength and residual strength. Okay. Okay. So that was about question number 2. Yes, that's about our question number two. Now let's move on to question number three. Okay. A consolidated drained triaxial test. Okay, now we are moving towards questions based on triaxial test. So the previous questions were based on direct shear test. Now we are moving towards triaxial test. A consolidated drained, please excuse me for a second. Okay. A consolidated drain traction test was conducted on a normally consolidated clay. Okay, so we are talking about CD test here. To give an overview, uh, when we talk about a triaxial test, there are two phases to it. First is the loading phase, and then we have, uh, sorry, the first is cell loading, cell pressure. What we do is we have this I, for example, have prepared a sample, and this is my sample. I will encase this sample in a membrane, and I will put it in the triaxial cell. So the first thing I will do is I will saturate the sample. I will put uh, cell pressure here, not to saturate the sample. The sample is already saturated. Sample is saturated using back pressure. But after saturation and everything, the first step is I will put cell pressure, which will be all around this sample, which will include here, 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 and here. And let me call this cell pressure as sigma 3. Sigma 3. And this will remain constant throughout my test. So in this case, there are two scenarios. One scenario is that I will allow drainage through the sample. If I have allowed the stage 1, this is my sample, and I have pressurized it under cell pressure. Now I have two cases. Drain, I can either allow drainage or I can restrict drainage from the sample itself. Okay, so if I allow drainage, what will happen is water will squeeze out of the pores and the volume of the sample will change. I will get a sample that is reduced in volume. If initially it was this much, I may get a sample that is this much if I allow drainage. And if I don't allow drainage, no drainage, what will happen is that the water is not allowed to move out. So the volume will not change, but there will be an excess pore water pressure development. Volume delta V is equivalent to 0, but delta U excess is not 0. And in this case, delta V, which is change in volume, is not 0, but there is not any development of excess pore water pressure. And if I allow drainage, consolidation is happening. So the first term here will be C, consolidated. And if I am not allowing this, this will be unconsolidated. So this was stage 1. Let me do one thing. So the first stage can be either consolidated. This will be drainage allowed, and it can be unconsolidated. Sorry, it can be consolidated or unconsolidated. Drainage not allowed. Okay. Remember, loading. What is the loading? It is cell pressure, which is delta sigma 3. Delta, why delta? Sigma 3 already due to in situ stresses, and now we are increasing this sigma 3. Next is stage 2 loading. What will happen? Here we will have delta sigma 1 or deviated stress. Now what we are doing, after the sigma 3, we will now load only in the axial direction. Till here, if it is clear, so what I did, I prepared a sample, I put it in the cell, I took and I applied cell pressure to it. Okay, that was the first loading stage. Now during the cell pressure, there are two cases. It can either be consolidated or unconsolidated. Now, for example, now the second stage after cell pressure is that I have to apply deviatoric stress, which is in the vertical direction. We will apply deviatoric stress. We already have sigma 3 or delta sigma 3. Okay. Now again we will have two cases. We can either again allow drainage okay. If we allow the drainage, it will be called drained test. And if we don't allow drainage, it will be called undrained test. Now, two cases in the first. Okay. Um, so, two cases in the stage 1, consolidated, unconsolidated. In stage 2, drained, undrained. So we should actually be getting consolidated drained, consolidated undrained, unconsolidated drained, and unconsolidated undrained. We should have we should get four cases, which is CD, CU, UD, and UU. But if you come to think about it, unconsolidated drain means that in the first stage you are not allowing any uh, drainage to take place, and in the second stage you are allowing drainage to take place. Now, if in the first stage the sample was unconsolidated, as soon as you will allow drainage, it will start consolidating. So technically, unconsolidated drain will not be a valid case, because in the second stage, as soon as you will start drainage, as soon as you will allow drainage, the consolidation will start to take place and it will be converted into a consolidated drain test. So this is not a case that we experience in triaxial tests. So basically, these are the three cases that we experience, that is consolidated drained, consolidated undrained, and unconsolidated undrained. In this, in the stage 1, we do not, we allow drainage, we don't allow drainage here. And in stage 2, we allow drainage, we don't allow drainage, and in this both cases we don't allow drainage. This is drainage. So this is about the different types of triaxial tests that can be uh, conducted in a lab. And to give an overview, unconsolidated drain test is very quick because you are not waiting for the consolidation to happen, which in case of fine grained soils where the porosity is, where the permeability is very low, it can take a long time. So this is a very quick test because you don't have to wait for anything. In this is fairly like in between these two, because in first stage you are even though you are allowing consolidation to take place, it will take time, but the second stage will not take that much time. But CD test is very time consuming because both the stages a lot of time take is consumed for complete consolidation and drainage to take place, especially in case of fine grained soils, clays that have very low permeability, and it takes a very long time for water to seep to permeate out of these samples. So that was about the types of consolidation triaxial tests. So let us now try to determine how. Now let us try to see how we calculate um, the shear strength parameters using a triaxial test. Let me clean the space a little bit so that we can get a good idea of what we are going up against. Okay, the question reads a consolidated drain test. So now when we look at consolidated drain, we will know that in stage 1 we have allowed drainage, drained. In stage 2 we have allowed drainage. This is the first thing that will come to our mind. Second thing that will come to our mind is consolidated drain, which means that there will be a volume change. And third thing is there will not be any excess pore water generation. So these are the things that should come to your mind as soon as you read consolidated and drained in both stages. Okay. A consolidated drain test was conducted on a normally consolidated clay and the results are given below. So the results are saying that in the first stage, when we took this sample and we applied a cell pressure which was sigma 3, we applied 140 kilonewton per meter square all around in the first stage. This will be stage 1. Then in the second stage, we increased the axial stress by 104. So this will be 140, this will be 140, and here this will be 140 plus 104 sigma 1. Okay, this will be sigma 3. Now we need to determine the angle of friction and angle theta that the failure plane makes with the major principal stress. Another thing about triaxial test is that we are not predetermining any failure plane. In direct shear test, what we did was we took this box and we filled a sample in this and we shared it along this plane. That is, we told the sample itself that this is the plane along which you have to fail. Okay, and it was always horizontal. But that is not always the case. In soil, the soil will fail along the weakest plane, isn't it? And you cannot determine, like, you cannot direct to the soil how it should fail. So when you are applying stress to the soil, if it is weak in shear, it will develop a crack in shear along the weakest plane. And in triaxial test, we do not dictate this failure plane. We're not dictating it. So what happens in our triaxial test is our sample will display failure cracks and these will be our true failure planes. Okay, and this is what we are to determine theta, major principal plane. Okay, okay. So let us try to solve this question. Keeping all this in mind. Now we know the formula for a normally consolidated soil. Okay, for normally consolidated soil, and it has been given that C dash is 0. Okay, so major principal stress will be sigma 1, which will be, as I told you, sigma 3 plus delta sigma. This will be 140 plus 104, which will be 244 kilonewton per meter square. And minor principal stress, which is sigma 3, as we already know, is 140 kilonewton per meter square. Now, if you look at the Mohr circle for a failure plane with C dash equals 0, okay, this is our tau and this is our sigma n. If you take this phi and let's write present um, how do I put this? Let's write sine phi will be equal to, this is the radius and this is the distance to the center. The radius of Mohr circle over distance to center. This is sigma 1, this is sigma t. And we know that radius of Mohr circle is sigma 1 minus sigma 3 over 2, and distance to center is sigma 1 plus sigma 3 over 2. So our sine phi will be sigma 1 minus sigma 3 over 2 over sigma 1 plus sigma 3 over 2. 2 and 2 will go. So sine phi will be 244 minus 140 over 244 plus 140, and this comes out to be 0 under phi will be sine inverse of 0.27, which is almost 15 point degree. Okay, so this will be our phi. C has been given as 0. Just a moment. Okay, so another thing that we should have discussed was effective and total stress envelopes. See, we go here, when we have undrained condition, the results that we will obtain are for total stress. Undrained will be total stress. In case of drained and consolidated, we will receive effective stress results. Effective stress, we will receive phi dash, C dash. Here we will receive phi u, C u. So there is a difference between these. Why there is a difference? Because you already know from the effective stress principle, when we are talking about the total stress, we are taking into consideration the neutral stress that is being projected by the pore water pressure. In case of drained cases, because the water is drained from this, the total stress becomes equal to effective stress models. So when we are talking about here, when we are talking about normally consolidated clay and we are talking about consolidated drained, so the fourth thing that should come to your mind here is that because it is a CD test, we will have effective stress values. Okay, and if we talk about sands, loose sands, and NC clays, they will have a C dash of 0. Dense sands or OC clays will not have a C dash equal to 0. Okay, so that is why we have taken C dash equivalent to 0 in this case. So the next thing is the next question we found the C dash, sorry, the phi dash. The second part is find theta, which is the angle at the failure plane makes with the major principal plane. And if we go back to your Mohr circle, we will recall, let me duplicate this. It should not duplicate. Let me add a slide. Let me add an empty slide. Okay. And let me just write this question again. For the first part, we determined this was equal to 15 degrees. Now for the second part, if you remember, when you draw your Mohr circle, this used to be your 2 theta, and this was your phi. From external angle consideration, we can say that in a triangle an external angle is equal to the sum of opposite angles, internal angles. External angle equal to sum of opposite two internal angles. So 2 theta equals phi plus 90. So theta is phi by 2 plus 45. And now your phi is about 15. So your theta will come out to be 15 by 2 plus 45, which is 52.5. So the angle that your failure plane will make with the major principal plane, this is the major principal plane, theta will be 52.5. Okay. Next question is find the normal stress and the shear stress on the failure plane. Now that is quite easy for you to do because we already know from the formula that sigma dash equals sigma 1 dash plus sigma 3 dash over 2 plus sigma 1 dash minus sigma 3 dash over 2 cos 2 theta. Okay, so this is on failure plane. This will be, and tau f will be sigma 1 dash minus sigma 3 dash over 2 sine 2 theta. So let's calculate this. Two 44 minus 140 over 2 plus 244. Okay, this is plus, this is minus 140 over 2 into cos of 2 into 52.5. So your sigma n will come out to be 178.54 kilonewton per meter square, and your tau n will come out to be Fine. 50.23 kilonewton per meter square. Okay, so sigma dash F was 178 kilonewton per meter square and tau F was 50 kilonewton per meter square. Okay, next part of this question is determine the effective normal stress on the plane of maximum shear stress. Now, what is the plane of maximum shear stress? If you see here, maximum shear stress is this, isn't it? And if you draw this here, how much will 2 theta be? See, using the same principle that we used for the previous question, let me draw it here. If this is the tau that we are talking about, let me actually delete this. Oh, if this is the tau we are talking about, and this is the radius, what do you think that the 2 theta will be? In this case, for tau max, 2 theta will be 90 degrees. Theta will be 45 degrees. In this case, our phi will be 0 degrees. Determine the effective normal stress. Now we need to determine effective normal stress. So sigma dash will be sigma 1. It will be the same, but now the theta will be different. What do you think? How much is cos 2 into 45? Cos 90 is 0. So sigma dash will simply be 244 plus 140 over 2, which is 192 kilonewton per meter square. In this case, sigma dash n at tau max will be 192 kilonewton per meter square. And if we compare it with previous results, you see the tau, one second, Here at failure, these were the values of tau, of sigma and tau. You see, this sigma is less than this. This here was 192, while our specimen fails only at 178. And for tau max is equivalent to 140 minus 104 over 2. Sorry, 244 minus 140 over 2. 52. So the tau max is here. This is 52, 192. This is tau max, sorry, sigma max, tau max, and here this is sigma f, tau f, which is 178 and 50. Okay. Okay. So that is it for this question. Let's move on to the next question. The equation of effective stress failure envelope for normally consolidated grayish soil is tau f is sigma dash tan of 28. Excuse me. Please excuse me for 5 minutes. Okay. So we will be a drained triaxial test. Remember, we have a consolidated drained. When we are talking about a drained triaxial test, it cannot be an unconsolidated drain. When it is drained, it has to be consolidated drain. It can either be consolidated undrained, it can be unconsolidated undrained, but when we're talking about drained, it has to be consolidated and drained. Okay, because there is no case like unconsolidated drain. A drain triaxial test was conducted with same soil at a chamber confining pressure of 100. So sigma 3 is equivalent to 100 kilonewton per meter square. And for the same soil, the effective stress envelope is tau f is equivalent to sigma dash tan of 28 degrees. So from here, we can see that phi dash is equivalent to 28 degrees. Calculate the deviatoric stress at failure. What we need to calculate is first actually sigma 1 we need to calculate, and from sigma 1 we need to calculate the sigma d, which is actually sigma 1 minus sigma 3. Okay, so since we just wrote sine phi equals sigma 1 minus sigma 3 over sigma 1 plus sigma 3. Let's try to redistribute it. Sigma 1 plus sigma 3 sine phi equals sigma 1 minus sigma 3. So we can write sigma 1 sine phi minus 1 equals sigma 3 minus 1 minus sine phi, or we can write sigma 1 1 minus sine phi equals sigma 3 1 plus sine phi, or sigma 1 equals sigma 3 times 1 plus sine phi over 1 minus sine phi. Sigma 3 is 100 and phi is 28. This would be 1 plus sine of 28 over 1 minus sine of 28. Let's calculate this. So sigma 1 comes out to be 276.98, approximately 277 kilonewton per meter square will be sigma 1, and our deviatoric stress, which is sigma 1 minus sigma 3, is 277 minus 100, which will be 177 kilonewton per meter square. So that will be our deviatoric stress at failure. Okay, now let's move on to the next question. This was fairly simple. The results of two drained triaxial tests on saturated clay are given below. Determine the shear strength parameters. This should be fairly simple now, isn't it? We just know that sigma 3 plus sigma d will give us sigma 1, and from sigma 1 we can either draw the Mohr circle, or we can calculate the uh, saturated clays, two drained. Okay, we can do one thing, is we can now we don't know if C is 0 because they are not mentioned normally consolidated. So let us not assume C to be 0. We can do one thing, and we can uh, draw, we will know what's two drain tests on saturated clay. So we will know two values uh, of Mohr circle. We can draw the circle. Let's do that. This is question number, I don't remember now, 1, 2, 3, question number 5, I guess. Okay, let's take it upon here. This will be question number 5. So we have been given sigma 3 and sigma d, and we can calculate sigma 1. Sigma 1 will be sigma 3 plus sigma d, and also for this. So we know sigma 1, we know sigma 3, and what is it that we require? We know the principal stresses. Okay, we can draw the circles. let me actually do that. Um, so I'll show you how to draw the circles for this. You know sigma 1, you know sigma 3, which means that you can know the center of the circle, which will be sigma 1 plus sigma 3 over 2, isn't it? And you can know the radius, which will be sigma 1 minus sigma 3 over 2. Now let us say that we are drawing this. This is shear stress and this is normal stress. Okay, and we are starting from here, and I'm taking x, 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 these values. Then what will be the y values for the graph for these? Y, 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 and y for me to draw the circle, which means I need to calculate this, isn't it? And what is it that I already know? I know this thing, I know this thing. So how do I calculate this? I know x, so this will be, let's call this C. Okay, and C, whatever my x is, for example here, this value will be, this is x, C minus x, isn't it? C minus x, and if x is greater than C, then this value will be x minus C, isn't it? Okay, and this value I already know. So the y value will be square root of radius square plus this x, x c square minus, and that is what I'm going to do here. Let me take the x value from sigma 3 is 70 and sigma 1 is 200. So I will take the x value as 70, 80, oh, 80, 90. I'll take this to 200. So this is for the first circle. And for the first circle, radius will be sigma 1 plus, no, minus sigma 3 over 2. And center, let's call this radius, will be sigma 1 plus sigma 3 over 2. Okay, and same is the case for specimen 2. Same is the case for specimen 2. So the y value will be square root of r square minus because I'm already taking square, so it's okay. It will be center minus x square, and let me fix this and this. Okay, so let's calculate y for all these, and for the second circle, let this be x1 and let this be y1, let this be x2 and let this be y2. I will take from 160 to 390, 160, 170. I'll take this from sigma 1 to 390, sigma 3 to sigma 1, 350, 360, 70, 80, 90. Okay, and the value will be, let me copy this, but instead of this radius, this and this. Okay, uh, okay, so let's first draw these. Let's call this circle 1 x and y. Okay, um, I should have taken smaller. Actually, let's do that. Uh, let's take smaller intervals. Let's say this is 71 and I'll take till 200. Okay, and this. Okay, and this was 82.5. Let me take 160, 160.5, 161. And like this, let me take till 385.5. Okay, now let us add some data. X value will be this, and the Y value will be this. This will be M1. Okay, now I will add M2, the second circle, for which we will have an X value of this. You see, we got a better circle. Uh, okay, here we can see this because this is coming out to be imaginary because this is going below the x-axis. So let's ignore that for now. Let us give the y values for the second Mohr circle. Okay, okay, and we can delete these. See, we got two good Mohr circles, two great Mohr circles. Now what we need to do is actually we should give the same scale to both the axes. It has to be on same scale. So let us take 0 to 400, 0 to 400. Or you can take major unit as 50 in this. Okay. Maximum, let's take 400. And here also, maximum, let's take 400. Okay. And we will draw a square. Mm, something like this. So on same scale, this will be our Mohr circle. And if we want to draw, insert a line let's insert a line. This is what you do geometrically, and we try to do this in Excel. I wanted to show you this in the last class only because that was more about the let me change the color of this so that it is visible. Basically, this is what we do. And then we check for the C and phi. That is how we plot the Mohr circle. And in this question, what is it that we can do? What we can do is we can calculate without the graph. So let's this will be sigma 1, isn't it? Sigma 1 came out to be 200. Here it was 383.5. Okay, so what we can write is uh, tau f1 is equivalent to c dash plus sigma f1 tan phi dash, and tau f2 equals c dash plus tau f2 tan phi dash, which means do we know this is sigma 3 at failure. Mm, we know sin phi uh, let me check what is it that we can do. Okay, so when we are writing 1 minus sine phi over 1 plus sine phi. This is basically or is it the inverse of that? Yeah, 1 plus sine phi over 1 minus sine phi is basically tan square 45 plus pi by 2. So when we write the equation for tau f and sigma, like from the Mohr circle, if we have this is 90, this is phi, and this is c. So we have sine phi is equivalent to sigma 1 minus sigma 3 over 2 divided by sigma 1, this is c cot phi, plus sigma 3 over 2. Let me check. Tan phi is, yeah, plus c cot phi. Okay, and this is equivalent to sigma 1 minus sigma 3 over sigma 1 plus sigma 3 plus 2c cot phi. This is sine phi. So sine phi is equivalent to sigma 1 minus sigma 3 over sigma 1 plus sigma 3 plus 2c cot phi. That implies sigma 1 plus sigma 3 times sine phi plus 2c cos phi over sine phi into sine phi equals sigma 1 minus sigma 3. This and this goes. So we have a 2c cos phi is equivalent to sigma 1 minus sigma 3 minus sigma 1 plus sigma 3 times sine phi. Okay, so what we can write is 2c cos phi equals sigma 1 1 minus sine phi plus sigma 3 1 minus sine phi minus sigma 3 1 plus sine phi. Okay, so what we write is sigma 3 1 plus sine phi equals sigma 1 1 minus sine phi minus 2c cos phi, and sigma 3 is equivalent to sigma 1 1 minus sine phi over 1 plus sine phi minus 2c cos phi over 1 plus sine phi. Okay, and actually let me write this the other way. Sigma 1 1 minus sine phi is sigma 3 1 plus sine phi plus 2c cos phi, and sigma 1 will be equivalent to sigma 3 1 plus sine phi by 1 minus sine phi plus 2c cos phi over 1 minus sin phi. So what happens is 1 plus sin phi over 1 minus sin phi is basically tan square 45 plus phi by 2, and cos phi by 1 minus sin phi is equivalent to tan of 45 plus phi by 2. You can calculate these identities yourself. So what happens is you will have a sigma 1 is equivalent to, let us call, okay, what we have is sigma 1 is sigma 3 times tan square 45 plus phi by 2 plus 2c 2c tan 45 plus pi by 2. So if we have two samples now, we will have sigma 1 of 1 equals sigma 3 of 1 tan square 45. Phi will be same for both, plus 2c also will be same, 45 plus pi by 2, and sigma 2 2 sigma 1 2 is equivalent to sigma 3 2 tan square 45 plus pi by 2 plus 2c tan of 45 plus pi by 2. And for 1 we have 70 and 200. Then we have 160 and 383. 200 is equivalent to 70 times n phi. Let's call that n phi, 2c root n phi. And then we have 160 and 383.5 equals n phi plus 2c root of n phi. So let's try to calculate. Let's first subtract these. This will be 3, 8, is this 383.5? Yeah, 383.5 minus 200 is 183.5. 183.5 equals 160 minus 70 is 90 times n phi. So this and this will go. N phi will be equal to 183.5 by 90. 2.039. So this is tan square 45 plus pi by 2 equals 2.039, and square root, that implies tan of 45 plus pi by 2 equals 1.43. So tan inverse 1.43, that implies 45 plus pi by 2 equals 55. Pi by 2 is equivalent to 10, pi is equivalent to 20 degrees. And to calculate C, let us just put 5 here and we will get 200 minus 70 into tan of 45 plus 10 square divided by 2 into tan of 55 comes out to be C also. C also comes out to be 20 kilonewton per meter square. So these are the values that we got from analytical results. And if we look at this, let us try to see what we are getting. I think this is around 20 itself because half of it will be 25. So yeah, 20 is the intercept. And if you look at the angle, this here is 250. Actually, let me insert a shape. This comes out to be almost 110 and 250. So what will be 110 tan of tan theta will be 100 but 110 minus 20. 90 over 250, 0.36 tan of tan inverse of 0.36 is about 19.9, almost 20. So yeah, our results are correct because if you want, you can match these. This is about this is about giving us the same thing. Here we have the perpendicular as 110 minus 20, this is 90, and this the base is 250. So the tan theta is 90 over 250, which is 0.36. So tan inverse of 0.36 is about 20 degrees. This is what we calculated from this. Okay, so this was about some questions based on shear strength. That is all for today, guys. Thank you very much. Let's meet next week.